The hope, the aim here is to sort of give everyone a bit of a taster really for writing a Wayland compositor. Based on our own personal experiences, we've written a couple of toy Wayland compositors, and also in the last month or so we've both been working on well, this compositor here actually, but this is a hybrid X and Wayland compositor based on Mux, so similar to Gnome Shell.
Similar to Gnome what?
Gnome Shell?
Gnome
Also
Shell.
the Gnome 3 shell. So the proviso is that a lot of this stuff is in development. In fact, just before FOSDEM, we had a meet-up with a bunch of the sort of people that are really focused on working on Wayland, and some of this stuff is already subject to change. But it should hopefully give someone who is interested in writing their own Wayland compositor a grasp on the basic things you're going to probably have to tackle and deal with. Okay, so I'm Robert Bragg. I work for the Intel Open Source Technology Centre. I work in the London office. I maintain a 3D graphics library called Coggle. I've done a bunch of work on the Clutter Toolkit, bits and pieces on window managers in the past, and even OpenGL drivers.
Yeah, so I'm Neil Roberts. I'm also on the Intel visualization team in London. So I work on Coggle as well, and I've recently just got involved in the Wayland effort. So I'll start by just summarising the current architecture you get with X. As you can see, the main point here is that the compositor is in a separate process from the X server. So that means that because the compositor is the thing that's actually displaying all the windows, the X server doesn't get a good representation of where all the windows are actually displayed on the screen. So if you're doing transformations and stuff on the windows, then the X server doesn't necessarily know about that. So the trouble with that is then if you want to do input onto those windows, the X server doesn't know where to send the events relative to the surface, because it doesn't know the transformations. And so it's also difficult to, because the compositor doesn't directly handle the outputs, it makes it difficult to, if you want to scan out directly from a buffer when it goes full screen, it's quite difficult to do that. So with the Wayland architecture, as you can see, the X server is replaced with just a single process, and that's the Wayland compositor, and that's the part that you will write, and hopefully we'll be able to help you with that with this talk. So the main thing you get from Wayland when you're writing the compositor is the Wayland server. This is mostly just a library to handle the protocol marshalling. So it doesn't actually include anything for doing the rendering, and that's all left up to you. But it does have some utility code for doing the input grabs and doing the data device, which will help you with doing cut and paste. So in Wayland, the clients are all in their own world. So that means that, so in the next application, you're allowed to ask the X server for all of the windows in the scene, and you can take a grab and receive all of the events for any application. But in Wayland, the applications are just trapped away in their own little world, and all of the events that they receive are all relative to their surface. So they don't even know where the window is on the display. So the reason this makes it great because the Wayland Compositor then has a lot more freedom to just transform the windows however it wants without having to find a way to describe that to the clients. Yeah, so in Wayland, the clients are king, so anything that doesn't need to be a shared resource is punted from the compositor into the clients. So things like doing the keyboard maps and keyboard repeats and the window decorations and that kind of thing that would typically be in the client. Yeah, and all the rendering is all in the client, so the client would just render to a buffer and give the buffer to the compositor. Instead of sending in X, you could send the commands to the X server and get the X server to do the rendering for you.
Okay, so I'm just going to run through a couple of the key concepts that you would need to know really before we get into more details that are key to Wayland. So the first thing is interfaces, events and requests. So with Wayland, the protocol is declared using XML, and you have objects that implement interfaces. So this is an example of an interface. The contrast there isn't too great, but I mean I don't really want to read through all of that. But you just got, this is kind of a nice example though, because this is actually something that's not in the core protocol, but it's an example of an extension protocol, and that's a complete protocol for dealing with X integration. But an interface is made of requests and events. The requests never have any kind of synchronous reply for them, so to avoid round trips, given that it's a multi-process IBC architecture, makes sense. But the compositor can send clients events to feed data back, and sort of pretty basic, really. You just describe names and types for all of the arguments for requests and events there. So yeah, each interface which has a name is associated with an implementation, which is an object. A Wayland Compositor advertises a bunch of interfaces. The first interface any client hears about is this interface called Wayland Display. It might get renamed to something like Wayland Registry later, something we've talked about. But basically that has an event called Global, which is able to just report out to the clients, here's a new name for an interface that you might be interested in binding to. So that's kind of how clients discover those implementations of interfaces. So this is a little snippet really of, in the compositor, what are you going to do to actually advertise a new implementation for a particular interface, just to register. That's a little V table there for the actual implementation, the second argument. Third argument is just a pointer to the actual object. And this last argument is to do with the binding to that implementation. So once you've advertised the implementation of an interface to all of the clients, then they might react to that by saying they're going to bind to that because they're going to use that interface. If they bind to that, then every time they do, then this callback here is going to get called in your compositor. So you can respond to that, but also this is a little snippet of what you would do in response to a simple object. This Wayland client add object API basically is going to allocate you a Wayland resource structure, and that Wayland resource structure is just to represent, well, it's the compositor's view of the client's view of that object, but it's the thing that pairs up that client is interested in this object. I haven't shown the fact that function does return a Wayland resource object there because I don't actually need it straight away. But if you're going to deliver some events immediately in response to the binding, we'd be using that straight away. But we'll see some examples later on.
The client object is a window?
It's not a window necessarily. There's all kinds of different objects that are important inside a compositor. I'll go through some of the objects, but one of those is kind of the surface, which is the window.
Okay, so the rendering architecture, so we'll just give a quick run through how the rendering works on both sides in Wayland. So to start with, in the clients, there's two main ways to render currently. So the simplest way is with SHM buffers. So this is where the client would allocate some shared memory, and then they can render directly into that memory using whatever drawing toolkit they want, like say the software backend for Cairo. And then there's an interface method to pass that shared memory buffer handle to the compositor, and then the compositor can copy that data out of the shared memory buffer into a texture and display it. So generally the client should probably try and avoid this method because it does imply a copy from the shared memory buffer into a texture, and it actually, they might even take away this interface. So EGL, so if you've not already heard of EGL, it's a platform-independent window system API. So you can consider it a replacement for GLX. You can use it to create a GL or GLS context and then render with it to either to a window or an off-screen buffer. So EGL is a platform-independent API, but it does have functions that take native pointers. So then it's up to the EGL implementation for how it interprets these pointers. So these are the two main functions that you might want to use that require a native pointer. So the first one is to create a display. So that's like the first function you would call when you're using EGL. You have to pass it a pointer to your native display type. So if you're rendering with X, this would be your X display pointer. And then you also need to create an EGL handle for the surface you're going to render to, and then you need to pass your native representation of the window there. So if you're running render X, that would be your X window. So in Wayland, the EGL implementation is used on both the client and the compositor. So then the EGL implementation, so the buffers are passed between the client and the compositor using EGL API. So then, because the EGL sits on both sides, the implementation is free to do whatever mechanism is suitable for that driver to pass the buffers across. So in Mesa, the EGL implementation will register a Wayland object which has an interface to pass the buffers across. So when you're using EGL in the clients, so you need to create an EGL display object, as I said before, and then you need the native display type. So we need something to fill in there when we're rendering with Wayland. So we can use the Wayland library to get a pointer to the Wayland display object, and then we can pass that pointer directly to EGL create display to get an EGL display. So then once we've got the pointer to the Wayland display, we can bind the default object, which is the compositor object. Did you call it display before? So that's the object. Once you've got that compositor object, you can call the create surface method on that interface, and that will give you a handle to a surface on the compositor side. So once we've got a Wayland surface, we need to get an EGL surface out of that so that we can use it under EGL. So we also, again, we need to find something to put into this native window type. So there's some Wayland specific API in the EGL implementation. So this EGL window create that creates so you get an existing Wayland surface that you created with a compositor interface, and then you just basically wrap that up with a width and a height to create a structure to pass to EGL. Okay. Yeah. So once you've got that surface with the create window surface, you can just bind your EGL context directly to that and then start rendering, and then everything else from then on is just directly GL or GLES. So on the compositor side, you just use whatever normal EGL platform rendering API you would use. So you can, for example, just use the X platform, and then you can get like a nested Wayland compositor directly under X. However, of course, it's not very useful to have Wayland under X because we're trying to get rid of X. But the EGL implementation does need to implement this one extension, EGL bind Wayland display. So that just has this one function that the compositor needs to call, and that just lets the EGL platform know that it should start trying to accept buffers from clients. So in Mesa, this registers the WLDRM interface so that the EGL implementation on the client side can get that object to pass the buffers across.
Okay, I'm going to just run through a couple of the key interfaces and objects. Yeah, by no means all of them, but some of the key ones to just give a taste of how we might implement some of those in Compositor. Okay, so Wayland outputs. Outputs are the objects that represent your displays. So under X, where you've got the XR and R protocol, and that lets you query the geometry of your displays, and it lets you set modes. This is only about querying information or sort of learning about the geometry and modes from clients. It doesn't at the moment allow you to actively control those modes. That's something that's not been developed yet. So this is a stripped out snippet of the interface description for this, just so it sort of fits on the screen. But the thing of interest here is just that there are a couple of events related to this interface. One event to report the geometry of the output, and one to report modes for that output. And so so I'm just going to show a snippet of code for how we would actually deal with a client binding to that interface. To say when they say they're kind of interested in that object, then so earlier on I showed you the highlighted red function, which is the callback when a client binds to a particular interface. So this would be a snippet of code that you might have in the implementation of that bind function for the output interface. And up the top there, where we've got this Wayland client add object, that's what we had in the snippet earlier, but you can see that we've saved a pointer to the resource here, which is the resource that just pairs up that client being interested in the object in the compositor. And we're going to immediately then just send out an event against that resource object, which is the geometry event, just telling you physically how big in millimeters that output is. It's just passing unknown for the make and unknown for the model in this snippet, but your compositor is going to use some kind of API for KMS, or so the kernel mode setting API, which we'll touch on a little bit later, and Jesse will give you tons of details on that later. But that'd be where you'd get a more sensible sort of name and plug that in instead. And then after that, we're just going to iterate through the modes that we've found for that particular output via the kernel mode setting API, and we're just going to pass those on as events to the client as well. So yeah, pretty simple. So yeah, the next object of interest is the compositor object, which we've already sort of mentioned a couple of times. This is pretty simple because there's only really one request for this interface. That's just to create new surfaces. Yeah, so the surfaces are the things that clients actually draw to. A surface doesn't actually have any associated geometry immediately once you've created that surface. It's not until you attach buffers to it that you actually get a colour buffer and some geometry associated with that surface. But this little snippet here is what's going to get called when a client actually requests to create a surface using that compositor object, using that compositor interface. I'm not going to go through all of that in detail, but yeah, you're going to allocate yourself a little internal structure to represent the fact that there is this new surface object for that client. You're going to fill in a Wayland resource structure, so yeah, that means plugging in the ID for the object. That means keeping track of the V table for the implementation of the surface interface, and we get to hang our own private data off of that resource, which hang whatever you like there really. Yeah, register that resource with the Wayland server, and then do whatever you need to do to sort of keep track of that surface with relation to your compositor object. At the very end, just put it in a list of surfaces associated with the compositor. Yeah. So the Wayland surface interface, yeah, you're going to have to do. This is an interesting interface. Clients use this to attach their colour buffers. When they render something using EGL, then they're going to call. Some of this is buried inside your EGL driver, as Neil sort of showed earlier. This EGL has a sort of black box component to it, and so different vendors might have different ways of dealing with how you attach buffers to a surface and send that over to the compositor. But basically, what's going on is that when you call swap buffers in EGL, then it's going to have to send a request to attach the back buffer that you've just rendered to a surface. Other things though relating to a surface are that the object can be destroyed. You can request for the object to be destroyed. That you can report damage against that object. So even though you do swap buffers and you're presenting a whole new buffer that you've just rendered, it might just be that you're only animating a small region inside that, like a little icon or so, and so you want to convey to the compositor that although, hey, here's a new whole buffer, by the way, only this tiny little region here has changed, so the compositor can use that information to make sure that it actually only potentially just redraws a small region of the display in response to that. So handling an actual attach request. Yeah, so this is a bit of a pseudo implementation, because actually in the compositors that we've implemented, a bunch of this stuff is really buried in some utility functions. But these are the key bits that really you're going to have to do and you figure out where they would fit in your own architecture if you're playing around with this. But you're going to use the EGL create image API to just, you can take the Wayland buffer that comes into this attached buffer request. It's hanging off the resource. The third argument is the Wayland resource for that buffer that got created by the EGL implementation. And you pass that basically straight into EGL create image. As long as your drivers can handle that enum for EGL Wayland buffer Wayland, then you're good. You've got yourself an EGL image, and it's just a case of generating a texture ID, bind that texture ID, use EGL image target texture 2D OES as a standard mechanism to make a geo texture from that EGL image. Destroy your EGL image now that you've basically got your texture, and hang that texture off of your surface, and you're going to then reference that texture when you come to paint your scene. So frame callbacks, this is an important aspect of any compositing environment really. This is something that X gets really badly wrong really. I mean, loads and loads of people have, well maybe not loads and loads of people, but there's a whole bunch of attempts at trying to solve this synchronization problem between clients in X and the compositor, and the problem is that you've got clients that need to render independently of the compositor rendering, and you don't want clients just going off and rendering at hundreds of frames per second, pegging your system when all you can actually do is display at 60 frames per second. So on X, yeah, you've got various attempts at using X-Sync extensions and whatnot to sort of deal with this, but no one's actually standardized it. I think Compass has one way, Enlightenment has another way, and the Mutter guys are now figuring out yet another way. So yeah, so under Wayland, there's a fairly simple mechanism here where the clients, once they finish rendering their frame, they're going to explicitly use one of the requests on the surface interface to create a frame callback object, and that callback object is just going to be collected on the compositor side, so that you might have like 10 different callback objects created by clients by the time they've all done their next frame. The compositor comes around to draw its scene, it's going to paint its stuff, and at the end of that it's going to emit a done event on all of those callback objects. So that just gives a really basic way for the clients to keep track of when the compositor's actually drawn the frame that's displaying what you just passed over to the compositor. This little snippet really just shows, I guess it doesn't really give you the context, but assuming that just before this function you just went and painted the actual scene for all of your outputs, and then you're going to loop through all of the callbacks that are pending, and you're going to emit the callback done event and destroy the resource associated with that callback. And that's really the sort of the basic mechanism for synchronizing clients. Another interesting interface is this Wayland shell surface interface. I'll skim over the Wayland shell interface itself isn't that really interesting. All that really gives you is a request to be able to get a Wayland shell surface object for a given surface, for a given Wayland surface. So a Wayland surface is really simple. You can attach buffers to it, report damage on it, but when you want to get into more interesting things relating to window management, so you want to be able to full screen a surface, or make it a pop-up, or make it transient for other things. These are all kind of high-level concepts relating to window management. Then that's what this shell surface interface is for. Yeah, so yeah, things like resizing a surface, making it a top level, making it transient for other surfaces. So that's if you've got dialogues and things, you want to make sure that it stays on top of other surfaces. Yeah, making it full screen, making it a pop-up. A pop-up is a special surface. It has some different semantics for dealing with input, so that we avoid grabs and things. I'm not going to go into that in detail really. But this is subject to a lot of evolution really, but a lot of things relating to sort of the EWMH extensions under X and the ICCM standards for dealing with how you talk to the compositor, for dealing with window management. Then this is the kind of thing that you deal with here, and potentially have further extensions outside of the core protocol for dealing with those kind of window management problems. This is really the bare essentials that are in the core protocol for dealing with the window management things that are going to just be common to basically every single compositor.
Okay, so on the display, so we just talked about briefly how you go about rendering without X in your compositor. The first thing is to use libgbm. Libgbm is a library for portably allocating kernel-side buffers. It lives in the Mesa source code. So the first thing you do when you're using GBM is to do GBM create device. That just gives you a device pointer once you've got that device pointer, you can use it with the EGL get display function, which I talked about earlier. So yeah, that takes that native display type, and you can pass the GBM device directly into that, so that you can get your EGL to render into GBM buffers. So there's this struct GBM surface. So GBM surface is it represents a swap chain of GBM buffers. So, so for example, if you're doing double buffering, it will contain 2 pointers to 2 GBM buffers. So this API is actually it's only just proposed. There's some patches on the MESA mailing list, so it's all in flux. So when you get round to writing your compositor, it will probably all have changed by then. So yeah, so we can just create our surface just with this simple surface create function. Yeah, and then once we've got our surface pointer, then again we can use this EGL create window surface function, and we can use the GBM surface as our native surface type. And then we've got an EGL surface representing that GBM surface, and we can directly bind an EGL context to that and start rendering with EGL directly into that buffer and into that surface. So once we finish rendering our scene, we'll just call the normal EGL swap buffers, and that won't actually make anything be presented on the screen. It will just swap over the 2 pointers to the 2 buffers in the surface. So when we want to present one of the buffers in the surface, we need to call GBM surface lock front buffer. That gives you a pointer to the front buffer from the surface. So then we need some way to display that, so we can use the KMS interface, which Rob will just talk about in a minute. Then when we finish with the buffer, we need to release it back to the surface, so that the surface knows it can reuse that buffer for a back buffer next time you call swap buffers. So yeah, to display the buffer.
Yeah. I'm going to go through this, a fairly brief description of kind of most of the thing, given that Jess is going to go through all of this in detail afterwards, and it's not very well documented in space, so I'm not that sure all of the details yet, so Jess is going to fix that. This is the key components you're dealing with in this API are the connectors, encoders, and CRTCs. I think it's actually maybe easier to go in the opposite order. Just this is kind of the order you discover them in, discover the objects in, but the data flow is more in the opposite order. So a CRTC is the component. If you've got a frame buffer somewhere in memory, then the CRTC is the thing that you program to give it a mode like 10 to the power 768 or so. And a frequency to scan out from that buffer, and it's scanning that memory at some frequency, and then it's going to palm that data off to an encoder, and an encoder is basically going to encode that according to some protocol to send over the wire to your monitor or so via a connector. So those are the kind of key things. The connectors are physical connectors on your laptop or so. So querying KMS resources, that's just this little API. That's going to give you at least the entry point to start discovering connectors. First step, looking for some connectors. This is just looping through the IDs that you're going to get from that resources structure. You're looking for something with the DRM mode connected. This little is connector excluded bit is just part of the details of our particular implementation, is that if we're looking for multiple connectors, maybe we're doing mirrored display or so, we need to just make sure that we ignore connectors we've already sort of found and dealt with. Find a connector, find then an encoder that can be used with that connector. You might have a whole bunch of connectors and only certain encoders can work with certain connectors. Just here, now the first encoder listed as working with a particular connector, So before we then go and program the CRTC for a particular resolution, we're going to just save the CRTC state, just because we're going to potentially be switching VTs later on, and we're going to want to restore that state. So yeah, save that state using that API, pretty simple. Then pick a mode, but I mean here just pick the first mode that can be used, but you might have some UI configuration mechanism that lets someone choose one of the valid modes, or you might be constrained because you're trying to find modes for multiple outputs that match because you want to mirror those displays from one frame buffer. But yeah, there'll be different constraints for your own system. Now, to be able to actually program the CRTC, you're going to need a handle to a frame buffer. So yeah, this is a DRM frame buffer, so this isn't the thing that really represents the bits for your buffer. You're going to get the bits from a GBM buffer, which is what we went through just before this. So assuming you've got a GBM BO, then you can pluck out the DRM handle, the KMS handle for that, suck out the pitch for that buffer, which you're going to then plug in, and that's going to then return you an ID for being able to set the mode. And then yeah, plug that straight into DRM mode, set CRTC, and hey presto, you've got yourself got your display set up. So yeah, handling.
So now you've got your compositor working, and the first thing you realise is now when you start up your terminal and run your lovely application in your compositor, and then you switch back to your terminal to press Control-C to kill that application, you'll suddenly realise it brings down the whole compositor because you haven't, because the TTY is still going, and it's going to handle that Control-C and send it to your actual compositor instead of to the terminal. So we need to do something about that. So we need to ignore input on the TTY. So how we're going to do that is there's this TC flush function, so we can open the TTY device directly and get a file descriptor on that, and then we can add that file descriptor to our main loop or whatever mechanism we're using, and whenever it's ready for reading, we'll just call this TC flush function, which will just discard all the pending input, so it won't go anywhere, it won't be handled. So we need to do certain things that only happen when RVT is active. So for example, we need to close all the EVDEV devices so that we'll stop listening for events if someone switches away to another VT. And we need to stop rendering so that, for example, if a client suddenly causes a redraw and we don't prevent it from rendering, it will just blat the buffer over the top of whatever VT you've switched to. And we need to set DRM master mode. I think that's some kind of mechanism for making sure that only one application uses DRM at a time, but I'm not totally sure because there's no documentation. And we need to enter and leave graphics mode on the. So yeah, I'll just show how to do that. So we can register. We can use this IOC tool to register for a signal to be sent to us whenever the TTY is released or required. Yeah, so when it's acquired, yeah, we'll get a signal handler to do all that stuff I mentioned. Oh yeah. So as an example of doing the enter and leave graphics mode, yeah, there's just this magic IOC tool you can call to set the mode to graphics, and there's also an equivalent enum KD text, I think, to set it back to text mode when the TTY is released.
Okay, so Wayland, right? This, if you want to write a compositor that has compatibility for X clients, then this is the way to do that. Yeah, so this Wayland is a way to be able to run a headless X server, and it's got a slightly modified video driver that's not going to take its own control over the kernel mode setting API. Instead, it's got a server-side compositor that uses the X composite extension to be able to redirect all of your top-level windows implicitly, and then all of those top-level windows are going to get presented back to your compositor as Wayland surfaces. So that's how you're going to then integrate them into your compositor. And your compositor is also going to connect to this X server as the window manager, or you could have potentially another process that is going to be the window manager for this X server. Yeah, so I'm going to run through how you might start X Wayland lazily. So the aim, ideally, is that you don't start X Wayland when you initialize your Compositor. You wait until some legacy client was actually loaded at the point, and then at that point you want to then load your X Wayland server. There's a few hoops to jump through, so let's just sort of give you a taste of those hoops. So step one is try and find yourself a free display number. You're just going to walk through /temp.x11 number, .lock, looking for a free lock file, checking for stale lock files, and as soon as you found a display number, then you're going to immediately just open up a Unix domain socket. This is the socket that clients are going to connect to, like an X client is going to try and connect to this. We're not going to, so this is just within your Compositor. You immediately open that, set it into the passive listening mode so that you're waiting for clients to actually connect to that. You can then put that file descriptor into your main loop, poll on it, wait for it to be readable, and that's the kind of indication really that some client has then tried to connect to that, and that's going to be when you start looking at forking your X Wayland server. So yeah, poll for the socket to be readable. Right, so say you found that the socket's readable, you're going to now prepare to fork and run X Wayland. So before you do that, we're going to make a socket pair here, and this is because we want the X Wayland server to actually be a Wayland client for your Compositor as well. The Wayland client is going to be able to then send you those Wayland surfaces for all of your top level windows. So a socket pair is like a Unix pipe, and we're going to get two file descriptors, and we're going to make sure that when we fork, we're going to fork, and we're going to give one end to the X Wayland server, and we're going to use an environment variable to just convey that file descriptor to the X server. Then we're going to wait inside our Compositor until we get the binding for the X server interface. So that's the callback I've sort of mentioned a couple of times that says that the client's interested in this interface. When we get that binding, then we know that the X server's kind of brought itself up, it's all initialized, and it's ready to start kind of dealing with clients. So it's bound to that interface. We react to that by passing the original Unix domain socket that we opened for listening for all of those clients. We pass that using a request, which is one of the requests for this X Wayland interface. Just gives you a mechanism to be able to, or rather, I guess it's an event because it's to the client, but there's an event to be able to pass that listening socket over to the X server. And then the X server is just going to take that and actually start, it's going to do the accept on that client connecting, and it's going to start handling any X requests from that client.
Is that another environment variable?
No. So instead of an environment variable for that one, that is actually over the protocol. The Wayland protocol gives you a way to pass the file descriptor over that. So it's an event that you send. So that's how that one gets conveyed. Just a little detail, just because I tripped up on this one, was that make sure that you flush the event out to your X Wayland server before you then go and immediately try and X open display or whatever to actually become the window manager for the X server, because if you don't do that, you've got yourself a deadlock. So you're going to connect as the window manager after you've got X Wayland up and running. And a detail here is that you've got two streams, two protocols. You've got Wayland surfaces coming at you and getting destroyed, and you've got X windows being created and mapped and unmapped and destroyed or so, and you need to pair those two up. So one of the other parts of the interface is for the X Wayland server to be able to send a request to the Compositor to tell the Compositor, hey, this surface corresponds to this X ID, so then you're in a position keep track of that relationship. Yeah.
So where do frames happen?
Where do frames happen? Well,